Hi, everyone. My name is Joshua Buck. Thank you for attending today's live stream with BrainChip and our expert network. We are going to be going over Neuromorphic deep dive into next-gen AI solutions, particularly around Akida and how Edge Impulse has enabled or brought BrainChip to the platform, and we'll be going into some deep technical content. Today, I have a number of presenters with me. Nikunj, next slide. I have Nikunj from BrainChip, as well as Sai, both solution architects. From our expert network, I have Naveen from Riken, and then, of course, myself is Joshua Buck. I'm a solution engineering manager here at Edge Impulse. We'll be discussing a number of topics today, including going over some previous technical content that we've had with BrainChip. And then BrainChip will take over and talk at depth about some important metrics to look at when designing models for their devices. We'll then hand it back over to me, where I'll be doing some Edge Impulse demonstrations, talking about some new features that are coming out in relation to BrainChip. And then we'll be doing demos, and of course, we'll have some time at the end for Q&A. So we've had a number of webinars and technical presentations with BrainChip and Edge Impulse together. Previously, we had talked about, from our launch, where we had first introduced Akida to the Edge Impulse platform. And it was really the first time that Edge Impulse has worked with neuromorphic models and neuromorphic devices. During that content, we talked about what Akida is, the AKD1000 enablement platform, and then we showed how we can do low code to no code deployments onto those devices. Then at Imagine last year, we had a tech session with BrainChip where they showed how you can take a convolutional neural network and then convert it over to a spiky neural network so that it can be compatible for devices like the AKD1000. And then we also had a webinar about benchmarking inferencing on Akida devices. Same kind of information that we gave also about Akida was presented here. And then we introduced something brand new, FOMO, for neuromorphic chips, in particular Akida. And that was the first time we had ported FOMO to a new device with a different backbone architecture in mind. Now we have some new content and some new features we'd like to show off. And of course, some technical information that BrainChip would like to present as well. So Nikunj, if you would, your presentation.
All right. Thank you, Josh. Hello, everyone. I'm Nikunj Kotecha, Senior Solutions Architect at BrainChip. And here at BrainChip, we are focusing on commercializing the Neuromorphic platform. We provide IP licenses, and we also have a reference chip as a development platform. Just to recap on Akida, Akida is a neuromorphic-based processor, and we focus highly on event-based processing. We have the capability to do advanced spatial temporal capabilities. We have event-based communication to support event-based processing. We perform at-memory computation, and we also support on-chip learning by doing event-based learning as well. And a lot of this material we have been talking about in the previous sections and previous webinars as well. So if you guys are new to BrainChip, I would recommend you guys to visit our old webinars and just learn more about the technology. Now, in this section, I really want to talk about what we see in edge devices today. Right? Edge devices are getting compact, they're getting smaller, and thereby they require battery that are long lasting. So every time they do any computation, it needs to consume less and less power, and this inferences needs to be faster. The edge devices are trying to be smarter enough. They want to be as quick as possible. They're also becoming smarter as including more and more features. And these edge devices may have more features from a software standpoint, and they also have more features from a machine learning standpoint. So thereby they also have maybe one model being deployed or more than one models to adhere to many of the different features or functionalities they have to offer today. So let's take a look at some example. In this example, we are doing some human pose estimation out here. And maybe your product is more of a fitness type of product where it's trying to analyze, the body posture and help some, training features on making sure the person is doing the right form. You're trying to guide the person on, hey, this is the right orientation, and so on and so forth. So you require some sort of AI models to recognize what the posture of the person is, and thereby you have to use some pose estimation type of algorithms. If I look at underneath the hood, what goes on in the machine learning pipeline, I do have an input image. But the first thing that I do need to take care of whether there's a person existing over there or not. So I do have to use like an always on type of model to person detection approach here. The next stage is if there's a person, then I would go ahead and have a much more deeper and accurate model that do get me points of the body. So do body pose estimation out here. And maybe I also have some features that recognize facial expressions, or just want to make sure that maybe there's some direction that the person needs to see. So it's maintained the right posture out there. So I also have some face detection models going out here. So you see there are many more models being deployed. And this is just a very brief example that I'm giving out here. Now, because of this nature, models become very large, and there are techniques such as different model compression techniques that we need to adapt to so that we can build an efficient solution. So one such technique is quantization. In quantization, every weight we use or tend to use fewer bits. Typically, you train in floating weights and you quantize down to int weights. The next technique is more pruning, where weights are packed more efficiently. So in this example, we're showing more filter-based pruning, where you're trying to reduce the number of filters, thereby reducing the spatial dimension of each of your layers within the model. And that reduces overall latency and power consumption. And the last stage is, activation sparsity. And we talk about activation sparsity a lot on Akida, because this is where we can really leverage the non-event values and ignore them completely and only focus on what really matters. So if you see in this example, we do a lot more fewer computations and still obtain a particular result that if you compare it to any traditional frame-based convolution, you'll get the same output out there. In quantization, there are basically two stages: post-training and quantization-aware training. And if you take a look at this quantization stage here, right, you have a scale factor and use the scale factor, during your forward pass during your training time, and then you adapt your float weights during your training of the models during your back propagation. And when you do that, you are going into the quantization-aware training stage, where it also accounts for the quantization error that is typically observed when you go down from float weights to int weights. In this case, we're using int4. In post-training, you typically work with calibration data to kind of find a reasonable range for your quantization bit values. And in quantization-aware training, you're kind of retraining your model for fewer epochs to find a good, reasonable range. And in that process, it also accounts for this quantization error that we're seeing here. Both stages can get minimal to no loss of accuracies. And typically what we have found is quantization-aware training gets you about the same accuracy as a float. And it also helps you to generalize a model a lot better compared to PTQ stage. And just a side note, this stage has been completely integrated into Edge Impulse as well. And Josh will probably go over some of these features during his demo. In activation sparsity, so if you think about a traditional frame-based convolution, you're doing this kernel and you have an activation map. You basically go over this kernel on this activation map row by row, column by column, and you get a particular result. In Akida, what we focus is we only do event-based convolution. So we only focus on the event values, and we still obtain the same result, but there is a significant reduction in the number of computations we are doing here. Now, in order to help this particular case, you can induce this kind of a sparsity effect in your training pipeline itself. There are some techniques such as activity regularization. So if you use these norms such as activity regularization during your training, You can observe that your model will become more and more sparse. It will have less and less activity in it, and it thereby produce less amount of effect out here. So if you see this example, we have a mobile net V1 on 1000 classes. If you induce this effect, there's kind of no effect because it is not reducing its activity. It's working over 1000 classes. But if you look at this next column here, we have 20 classes here. In 20 classes, you see a significant boost because the model doesn't need to have that much activity to recognize or classify between 20 classes. And you see the same observation out here in when it's just 2 classes as well. So all of this directly affects your power consumption, and it also affects your latency. Because remember, the less amount of computations you do, the less power it consumes, and the faster you can have your inferences completed on every single sample. And this is where Akida really shines out, because a lot of traditional DLAs out there may not be able to leverage the activation sparsity. They have some techniques to leverage the weight sparsity, but on Akida, because of its neuromorphic design, we can leverage both the weight and the activation sparsity as well. With this, I'll hand it off to Josh, who will be sharing his insights on the demo and talking more about the features that we have integrated. Josh?
Great. Thank you, Nikunj. All right. So today I'm going to go over some new features that we have in Edge Impulse. I'm also going to discuss some information about how we can size our models for the various IP configurations that can be coming with Akida. Just as a reminder, like anything else in machine learning land, right? We had to do a number of steps to get a model trained for a device. Okay, so assuming you have your test data set and everything like that, and your training data set, and you've done your feature generation, you have to go choose your model, right? In previous webinars and in our documentation, we discuss, what kind of models we have that are compatible with Akida, and how you can go about selecting those and then tweaking them, right? So when you're trying to figure out what will run on Akida, and then how you would design it for your engineering constraints, you got to go train a model. You start from there. Then we have in the log in the past the output of the profiling information, right? We talk about MPs and max, and then even some of the model sparsity information that Nikunj had just discussed, right? But we brought those to the forefront now. So we have now a new way of visualizing that information so that you can see that more easily. But really what's happening on the back end is that we've exposed that through the Edge Impulse API, and now it's pervasive throughout the platform. And so this has enabled us to add Akida to Eon Tuner. And now this is a brand new device that we can go and compile and run multiple training jobs at once to go in through a search page and efficiently step through a bunch of Akida models. And then you can go and select which one fits your design. I'd like to do a demonstration of that and kind of walk through Eon Tuner. So for those who are not familiar with Eon Tuner, we have a tool that is that allows you to efficiently work through a bunch of different models at once. So let's say you have the following problems, right? You already have a DSP design that works well for your application, and you don't want to change it, but it does a really good job of picking out features. All right. Or you have a base model, but you want to go explore different configurations of the model. For example, that you want to go change from RGB to grayscale, or you want to change the number of convolutional layers. Okay. What you would have to do in a lot of platforms is go make a tweak, save that off, run the model, run the training job, and then, save each configuration of that model, and then go do a bunch of A/B testing with that. Eon Tuner automates that process. So we have some documentation about it, and we use it a lot for a lot of our other devices. We have now ported it so that it actually compiles Akida compatible models as well. But there's a lot of information here about Eon Tuner that's in the documentation. I'm going to go through some of the more important highlights that you need to use in order to get it working with Akida. This feature will become available in the near future. Right now, it's in a very early access state. So if you have requests for using it with Akida, do please reach out to me at joshua@edgeimpulse.com. If you're familiar with some of our more popular example projects, we have this one for Akida called image classification, and it's really just classifying on a plant or a lamp, right? And telling what's inside the picture. So if we look at this data set here, right? So, that one's a plant, and then we have this one, and the image will say, okay, that's a lamp, for example. The model that we chose to train on is one from Akida, from BrainChip's model zoo, right? It's an AKD1000 model. And when we trained it here, we got 97% accuracy quantized. Now, this is actually Akida based accuracy on the validation data set. If we look at the float, you can see that they match really well because Akida has done an amazing job with MetaTF, their framework for converting models from traditional neural nets to spiky neural networks. And when we do that quantization aware training step, which is built into these different learn blocks here, we can regain some of the accuracy that might have been lost during normal or traditional quantization techniques. But during that training, there's some information that we extracted from MetaTF. And now we brought it to the platform so that you can see it as well, right? So if I come over here and choose Akida again, we can go and see different information. For example, the number of MPs that the model used. This is directly correlated to how big of an IP footprint do you need for your design, right? And then we have the max, which is a sense of like how many operations is it going to take to run that model. And then of course the model sparsity, which has a corollary to the amount of power that you're running on the device, right? And since we've added that to Edge Impulse, we then have now enabled the ability to use it with Eon Tuner. So this is an Eon Tuner run that I've done previously. Each one of these boxes that you see here is a different set of configurations for DSP, the DSP features, and the model itself. And then we also expose and show off, the Akida specific parameters as well. Here I present, maybe 10 or 15 different models. This took a couple hours to run, right? Because we launched a number of different training jobs and run it for different epochs and training cycles for each one of these configurations. Let me go into the search space and then how we would configure such a thing so that we can be more efficient in our search. So just like any other normal Eon Tuner configuration, we have this Eon Tuner setting page. And we can come in here into the search space and edit it. We have a number of different templates, right? So I can load a template for vision or a blank one. And then you can even load kind of sub-templates or sub-skeleton code for different configurations. Like I want to go change the input size, or I want to go change which type of learn block it is. Or maybe I have organizational specific things. Like, so if you have an enterprise account with us and you've made your custom DSP or your custom learn blocks, you can go and choose those as well. This might be coming up a little small. I apologize. It looked bigger earlier. But what this Eon Tuner setting is doing is it says, okay, change the image dimensions from 160, 160, test that one, and then also test a 224 by 224. And then also test the ability of test the models for either RGB or grayscale. So you already have multiple configurations. For example, 160 RGB, 160 grayscale, 224 RGB, 224 grayscale, right? Then let's test a Akida block for just basic classifiers. So this one is going to go test a number of different convolutional layer configurations. So we do 2D columns. So we have 2-layer, a 3-layer, and a 4-layer model that we'll do. So now you can imagine the search space is 160 grayscale and RGB with all those different options, and 224 RGB or grayscale with all those options. And then you can even further specify the amount of training cycles you want to work through, and then even some of the dropouts as well for model training. Then if you have models that you want to transfer learn against, we can pick those out as well. So we have a number of Akida models in the platform, as well as other TensorFlow models. And it gives you tooltips here to go and so that you can go write which one you want to test against. So we have then another set of configurations. Again, we're testing 160 and then 224 RGB and grayscale. And then I decided to test two different AkidaNet models that were both pre-trained on the ImageNet data set. And then I just had chosen them to keep one learning cycle and 20 training cycles each. So in general, we had two different groups here. A basic classifier with just a number of convolutional layers, and then one that's a transfer learning on an ImageNet AkidaNet based model. So I'm not going to start the job again because I'll clear out what the results I do have already. But in typical, it could launch, about 30 jobs, and there is a time limit there. Again, contact Edge Impulse if we need to bump up the time limit if you have a big search space. But what we can see is if we go back to the original model that we trained on, all right, let's take a look here. So if I'm going to click, it just takes a second to go back to the previous page, apparently. Well, we'll wait for that to load. But we can see the different models that we have here, right? So the top line number may all look the same, but each configuration is different. So take a look here. Oh no, let's go back one page. Here we go. So if we go back to the different models that we have here, we have a model that says it's 96% accurate. And we look at the confusion matrix. It looks pretty good, right? 100, a 92 on classifying plant, 93 over here for the unknown. And this configuration was an AKD1000 based model, RGB 160 by 160. And it takes about 25 MPs and has a sparsity of 69%. But let's say that that doesn't fit your design constraints. So let's take a look at this next one over here, and this is sort of by accuracy. It uses a significantly smaller amount of space, and the sparsity has gone way up, right? So what's the difference between these two? So this one here in the middle operates on the grayscale, right? So we're lessening the amount of features that we're sending into the model. And it's just a few convolutional layers as opposed to many that's in the AKD1000. And also, since this one's not a transfer learning, right, you might notice that the accuracy is a little lesser here as well. So maybe that gives us a hint that says, okay, since it's a raw model that's untrained, we maybe need to increase the number of training cycles for it or change a bit about our data set to get and regain some of that accuracy back as well. And then other jobs that may have run or may not have passed, we tend not to show those off. They're filtered out from the list. And then you can kind of go through here and see all the various trade-offs and various runs that Eon Tuner had done. If you want to use that model and actually run with it on device, all you have to do is click select, and then you can come back down to the deployment page and select the AKD1000, and it'll generate for you in a no-code fashion a precompiled binary for your Linux or Raspberry Pi x86 or ARM device. Let me show you another Eon Tuner run that I was working with one of our developers. This one's on a Google speech command set. So here we have a number of different Eon Tuner runs, but in order to work and change, let's say, the amount of QAT or even the activation and quantization levels, we brought some of those parameters out to the forefront so that we can then go iterate on those as well. Again, these are early access, early preview kind of things about what's to become coming out with Edge Impulse and BrainChip. So switching gears, we recently released a few different blogs, and we have a couple different demonstrations that we'd like to show off where we can highlight how we're able to prove that we can show and match the Akida accuracy specs from their Model Zoo in the Edge Impulse platform. So we have, if you have it over to edgeimpulse.com/blogs, we have a new blog that's out called Benchmarking with Akida and Edge Impulse, and where we validate Akida's models and show that we can get that same value from the same data set and run it on device. So there was a number of different models that we chose from. All right, here's Adam Taylor, someone that wrote this blog. I'll demonstrate that person detection capability today. But the real interesting information is down here at the bottom, right? So we have this table where if we look at what BrainChip has posted as their accuracy numbers, we're able to represent as well in project form this very close to those same accuracy numbers. So in other words, we take the same data set, we start from the same base model, we train and quantize it like Akida does, and represent that, we too can produce the same results between the platforms. So let me do a live demonstration of the visual wake word. If you're not too familiar with the visual wake word data set and what it's trying to do, all it is an image classification program or model that detects when a person is in the frame or not, right? And it should do a very good job of that. You can, Nikunj had a slide earlier where he showed multiple models that you need to do in order to run on an edge device. And one of the first models that you would need to do in this always on scenario, which would typically be a low power scenario, is just detect the presence of a human being in a frame. So I got that today. I've already downloaded and deployed the model to my system. So it's sitting here as an Edge Impulse EIM file, and I'm going to run it on device. And then I'll switch over to this other window where we can kind of preview the frame. So here it detects me. It says I'm here, right? I know this demonstration is very simple, but it's a very big data set, and it's a very difficult model to train and get right the first time, unless you developed a good and efficient model for it. So if I move out of the frame, right, it doesn't see anybody there. And just to prove that it's not detecting other things just in the frame itself, right, I can put that in here and show that it's generally uncertain. It alters between the two. We typically say put a low pass filter on the inferencing results because they come so fast. But nonetheless, right, this is how I'm demonstrating that we're picking up, person versus not person on these data sets. I would like to hand it off to Sai, who has a demonstration on FOMO, and then eventually we'll hand it off to Naveen as well, who'll be going over his expert network project as well.
So yeah, I'm Sai Chaitanya. I'm also a solutions architect at BrainChip. So I worked on a project called vitamins detection on Akida. And this is basically based off a FOMO model, which is first objects, more objects. In real time, it basically tracks and counts multiple objects in real time. And we have utilized this particular model on Akida. So for that, for what I have done is I'm going to just follow through you the steps which I have done. And the first thing is I've collected the data, like samples. So first I created my own data set. So with the Edge Impulse platform, so I was able to collect around like 5,574 samples, where you can see here different, this samples consists of 4 different vitamins. So for my use case, like I'm going to detect 4 different vitamins, namely vitamin B, vitamin C, K2, and zinc. And also using the data acquisition tool, I was able to label the data appropriately, where you can see here the appropriate bounding boxes for that particular vitamin. So this is vitamin B, zinc, K2, and vitamin C. So once the labels are done, and we're gonna go for the impulse design. So this is basically where you can just getting your machine learning pipeline ready for before the training happens. So where you are basically setting your input access for the images, and also adding your processing block for the image, and also choosing what kind of algorithm that you wanted to choose, where it have the option of, if you click on this, you will have multiple objects. So where I have chosen the BrainChip one, which is specifically designed for our reference SoC. And once the impulse design has been created, you can save the impulse, and you can go for the image next block, where you can generate raw features, like features from the images, which whatever you have collected, and the label data here. So once this particular generation of parameters is done, the next step is going for the training pipeline. So in here, you can see that in the training pipeline, where we usually call this visual mode, we have chosen our own AkidaNet model with alpha 0.5 with the input resolution of 224/24/3. And you can also have different various models, but for this particular application, in order to deploy and run the model on Akida, we have chosen the AkidaNet model, which is our own version of MobileNet V1, which is much more efficient and best suited job for this particular application. And when we ran the application, you can see the backgrounds here. So in the back, it can show you the confusion matrix, where it actually have a different pipeline, like your metrics, like for how much it is basically classifying right samples versus it's like a confusion matrix. So it's showing you for the K2, vitamin B, vitamin C, and zinc, all of the samples. So this is not like ultimate accuracy or something. So if you want to get more accuracy, or so, you can also edit the code, and you can just try change the parameters like learning rate and also number of training cycles to get the desirable accuracy that you wanted to do. And the next part of this is where you can just go for the model. There are a lot of blocks in here where you can just retrain the model, or like Joshua mentioned, you can go for yarn tuner, like where you can set the parameters for, where I haven't done it here, but you can just choose your target and you can.
Yeah, sorry, sorry to interrupt. For Eon Tuner, object detection is something we're still working on a little bit for BrainChip.
Exactly.
Yep.
So with the BrainChip, it's still the work is going on. Once it's done, we're going to test this feature and see how it efficiently going to do the job. And then you can go for model testing, where you can see, classification, how this happens. So in here, I've just, when collecting the data set, it basically, divides the samples into training and testing. So once the training has been done, you can just try to see how the testing is going to happen, where the accuracy here is around 94.7, which is like 95% accuracy. So once the live classification, like all the testing data has been done, I have chosen, we can go for deployment, where you can, like Joshua mentioned before, like you can just download the pre-compiled binary file. So depending upon what kind of system, Linux system that you have, for us, we have two different types of enablement platforms. One is Raspberry Pi based, and another one is Intel x86 based processor. So I'm currently working on Intel x86 based processor. So I have chosen that particular system to download the binary file. So once the binary has been downloaded, I think there is documentation in Edge Impulse platform, like what kind of packages that needs to be installed before running this file, like from both Edge Impulse side and BrainChip side. And it's very easy to follow. So once it's done in your Python environment, if you run the EIM file, the output would look like this. I'm going to try to show you the demo on live. Actually, I have the next to me. So if you can see here, so now this is basically a carousel where this vitamin K2 is there. It's already classifying it. Just for the distraction, we have kept schedules where it is not picking up the schedules. It's only focusing on the vitamins that is there. So here you can see the conveyor belt, and where I have lined up all the vitamins next to on top of conveyor belt. So I'm going to try to start the conveyor belt so you can see how it basically tracks the vitamins, and also you can see below the power consumption that is happening here. Let me go and start the conveyor belt. It will be a little bit sound, but I think it should be. So now you can see the vitamins are getting classified: brain, vitamin B, vitamin C, zinc again, and then vitamin C.
Gotcha. Side was coming in a little choppy there, but what we have here is that conveyor belt off on the side is coming in.
Yeah, basically the problem is like it's all the vitamins are the closed, right? So which is why it's basically doing that issue. So there is no guarantee that it's going to fall on carousel properly. So if you have a proper bowl or something, it will just land accordingly. So this is just to replicate the real world situation out there in big pharmaceutical industries and everything, where they have huge conveyor belts where it will be displayed a lot of vitamins there. And it's just, we are trying to replicate that scene. So you can notice if you go for the performance metrics here downwards, so it's like showing like around 6.8, 6.97 milliwatts. It's very low power consumption. And also the FPS is good. And also the latency is around like 7 and 8 milliseconds. So with this pipeline, the entire machine learning pipeline, which like Edge Impulse offers, and with the model that BrainChip has, and with BrainChip's technology, so we can achieve a more efficient, efficient model, and which actually saves you a lot of power. And so this is what I would wanted to show the demo here. And I'm now gonna stop sharing my screen. I'm gonna hand it off to Josh.
Yeah. Before you go, Sai, just one point, was that the Skittles weren't being detected because the model wasn't trained on that particular
exactly. So the focus here is to just to focus on the vitamins. Vitamins are the object of interest here, because let's say, for example, in real world situation, if the conveyor belt has been happening, if there will be some kind of debris out in here, so we don't want to focus on that kind of unnecessary data. So that's the idea here. So when I collected the data, I've introduced different backgrounds, and also introduced various other objects other than vitamins. So just to make the model more efficient, so that it only focuses on the particular objects of interest.
Indeed,
so that's
indeed.
Yeah.
So we had a question here from the crowd. It says, does the output of the model include the relative coordinates of each location in the camera frame? Yeah, I'll take that one. So this is our normal, so this is Edge Impulse FOMO through and through, just on a different backbone that's compatible with Akida. So the output of the model, if you either use the EIM and call into it with one of our SDKs, or if you compile it yourself, right, does have the grid and coordinates as well as part of the inferencing struct. So if you look at the command line that was running in there, so I didn't show it, but there was a command line that was coming out in the background, and it gave the coordinates of where that location of those particular objects are, the label, as well as the inferencing score, how confident it is of the particular object that it's detecting. Great. So I think now let's hand it over to Naveen, who's also from our expert network. He's here is to talk about his blog, which is traffic monitoring. Naveen, we have a lot of time for you, so go ahead and take the screen and do your presentation.
Hello, everyone. I'm Naveen Kumar, and today I'm going to talk about a project which I worked with Edge Impulse Expert Network recently, and it's about the traffic monitoring with BrainChip Akida. So before that, a little background. So I studied information technology, computer science, and bioinformatics. And I'm working as a researcher at a research institute in Japan, almost like it's 15 years. And mostly I'm doing microbial genome data sequencing analysis. So that's my day job. But I have also a side gig as a hobby job. And it's all started with blinking an LED on Arduino Uno and experimenting with Raspberry Pi in 2013. And I'm a very much active project contributor at Hackster, Electromaker, and Hackaday. And I have won various contests since 2020. And I'm a very much active community member at Machine Learning Tokyo. It's a very big and large community here in Tokyo with more than 10,000 members till now. And as a team, actually, we won a Signet gold medal with this community. And I was also a winner of a Google TensorFlow Lite for Microcontroller Challenge in 2021. And most of my project actually is related to the machine learning at the edge devices. So why do we need for a traffic monitoring? So traffic monitoring actually help us to identify congestion hotspots and prioritize the signal retiming or lane changes. And we can implement traffic circulation changes by comparing travel time under different tracking travel times. And we can observe road safety. That is important. So actually, I am using one of the hardware from BrainChip Akida development kit. And this hardware kit actually consists of an Akida PCI board, which is actually mounted on the Raspberry Pi compute module for input-output board. And this kit comes with a pre-installed Ubuntu. And it's actually ready to go kit. So we just have to deploy the train a model and deploy onto it. It works out of the box. So before training the model, we need to collect the data. So I'm working on the vision model. So in my area, actually, I cannot capture the video of the moving traffic using drone or some other means. So actually, I used a license-free video from pexel.com. And from that video, I extracted every fifth frame to generate a data for training. So I used OpenCV Python script for that. And using the Edge Impulse command line tool, it was really quick and easy to upload all the extracted frame to the Edge Impulse Studio. So after the data collection, actually, we need to level the data. So here I am displaying GIF. So actually, it's a manual task. So I have to actually create a bounding box around each subject of interest. And in this case, we only have only one object, that is the vehicle. And once you select one class, so the Edge Impulse Studio gives you auto suggestion, kind of like auto entry of the level. So it was quick, easy after a few frames. So after the leveling the data, we need to design a impulse. So for designing the impulse, first we have to decide on the data pixel size of the image. So I have chosen 224 by 224 pixel size of the image. And as a DSP or pre-processing of the image data, we have chosen the image block. And the third block is actually the object detection that is specific to BrainChip Akida. And after the creating this impulse, we need to extract the feature. So this is also a quick process, because from the image, the data feature is actually the pixels. So it was really easy using the Edge Impulse. And after the data extraction and feature extraction, we need to actually define the model architecture. So we already have chosen the Akida FOMO model from the BrainChip, and it's just we are not using any customization of this model. We are using this model as it is, and Akida FOMO model actually uses an architecture that is similar to a standard image classification model, which splits the input image into a grid and turns the equivalent of the image classification. So actually it works on each grid independently and parallelly. And by default, the grid size is 8 by 8 pixels. And that means for a 224 by 224 image, output size will be 28 by 28. So that is the output of the model actually. And you can see the grid as like a red color in the image. And after the training, actually, we have a training accuracy matrix. So you can see in the confusion matrix, and also the accuracy of the F1 score is 90.6% for the quantized integer model. And for the quantized Akida model, actually, accuracy is better. So actually, we have chosen 94.0% accuracy model for deployment. And for the deployment, actually, we need to download the Meta TF model, which is automatically generated by the Edge Impulse Studio. And we can download it from the Edge Impulse Studio's dashboard. And we need to copy this Meta TF model to the Akida development kit. So we need to we can do the SCP to copy the model to the Akida development kit. And to run the inferencing, actually, I'm using the Akida Python SDK that is really easy to integrate this model with. And I'm going to show you a quick demo of this. So using this Paxel.com video, actually, I'm running the inferencing over on it. So let me play it. So you can see the vehicle is actually identified accurately. And so this video was taken from a drone from the aerial view, and drone is actually, I think, coming closer to the ground, and the vehicle size is getting larger and larger, but still the model works quite nicely. And you can find all the information of this project at the given link. And you can also see the inferencing speed is under 40 millisecond, and the power consumption is under 40 milliwatt. That is very low powered. So that works quite well. Thank you for your attention.
Thank you, Naveen. Awesome demonstration. Naveen, if you can stop sharing, I'd like to share off one more piece of information, and then we'll open it up for general QA. So let me go back here to slide from that. I'd be remiss to tell you, or not to tell you, about our upcoming event here in September, where we'll have a lot of our partners, as well as BrainChip, at the event. It's Imagine 2023. It'll be September 27th in San Jose. It'll be streamed online. There's a registration link here through Bizibo. If you want, you just head over to Google, type in Edge Impulse Imagine, and you should be able to get to this page. It is a free online event for those, and you'll get to learn a lot about our technology, about different edge use cases. We have a number of different speakers, as well as a number of different partners that will have demonstrations at the event. So now I'd like to open it up to any kind of questions that people have. If you do, just feel free to type them in the chat, and then we'll be happy to answer them. So Nikunj, I did have one question about model sparsity and then also the MP configurations as well, right? Is there a quick rule of thumb for sparsity and then like power usage and power consumption, or is it just generally correlated? Is it a power rule? Is it linear correlation? That kind of information.
What we've observed, it's not that linear because it traditionally also depends on where the sparsity is also occurring and in which layer it is also occurring. Whether if it's just glimpse of non-events value then you won't see much effects, because if you think about convolutions, how they operate is, you have a kernel and it has to do all those computes, right? And if it's within that block, if there's just one or two non-event values, you don't see that much effect in power consumption. But if, let's say, if the kernel has to skip over an entire, maybe a row or maybe a column, then you start seeing more effect on power consumption, and as well as latency as well. So it depends on where the sparsity occurs, and also on what layer it occurs. If you find out it's more, typically when you see a network on a layer to layer basis, you'll find there's more activity at the top of the network and there's less activity at the bottom of the network. So if you're really trying to optimize your model for sparsity, you may want to just focus on the top segment of the model to find it. Maybe I can induce more sparsity there, or you can work overall throughout the network as well.
Gotcha. And a corollary follow-up to that. So when you say you work on the top part of the model, you're saying, let's say you take an input image and then you try to feed it down, and if you change the dimensions of the input image down to maybe like a 96x96 or 32x32, that generally would that necessarily increase sparsity, or we're really just now reducing the feature? So we're not talking about sparsity anymore, but we're just talking about less max overall, so less power on the device.
Yeah, so overall,
there's a question there, but that was my comment. Yeah,
you kind of answered your own question. So, but I mean, if you reduce the input dimensions, you're reducing your max in general. So there's a power saving right about that. But yeah, I mean, in general as well, you will see a drop in your accuracy because you reduce your input dimensions. So you've lost a lot of information out there. But in some cases, as you show in Eon Tuner as well, maybe that's okay. Maybe the model is like too big. It's kind of an overfitted model, and you want to prune it down. So that way you can really work well with the Eon Tuner stuff and finding out, hey, if this RGB works, or if this grayscale works, or should I just prune down one of the layers or one of the filters that I seen earlier, right? So reduce that from a spatial standpoint as well. So yeah, Mac you reduce, and then you can adapt to other optimization techniques to make sure your power and latency also conserved.
Which is why you need Eon Tuner to run all those jobs in an automated fashion. Yeah. A couple of questions have come in the meantime. So a person's asking, what are the hardware requirements for the host device? So we have these enablement devices, right? And these are enablement devices eventually for when BrainChip is on some chips. Do you have some information about that? And I'll be happy to share the screen if you want to bring up BrainChip's website for that information.
Yeah, so I think one of the question is, what's the hardware requirements, right? So when you think about, so our development board, which is the AKD1000 mini PCI board, it has our AKD1000 chip on it. And so that's a chip that has our IP. And typically when you want to deploy your applications, this board is nicely plugged into any of the boards that have a PCI slot into it. So we ship 2 development kits, which is an Intel x86 box, and the other one is a Raspberry Pi Xbox. So you work with an ARM type of host as well. So these are really more of a reference kits and development platforms for our developers. Akida doesn't require to be specific with it has to be an x86 or it has to be an ARM. It is independent. It can even work with a RISC-V processor as well. And regarding your Linux platforms, you can even work with bare metals, RTOS, any other operating system that you may have on your host.
Gotcha. Thank you. And then somebody's asking about the information about, the technical information for the Akida processor, type of models and neurons that you can run on it, where it's asynchronous type of technology, asynchronous versus synchronous. I assume you'd find out also through BrainChip's website a bit?
Yeah, so there's a lot of information on the BrainChip website, that we have a couple of white papers as well. I highly recommend, if you guys are interested to learn more, reach out to us at sales@brainchip.com. So that way, we guys can get in touch and we can help you learn more about the platform. If you want to learn more about MetaTF as well, you can visit brainchip.com/developer. So that's where you can, play with the software along with it. And if you have the dev kit, you can work with this, or you can also work with the Edge Impulse platform to get collaboration done with the development platform.
Yes, I'll say MetaTF is really great to work with. In previous technical content that we demonstrated with BrainChip, we have integrated MetaTF inside Edge Impulse so that you can develop your code in Keras and then call into MetaTF functions specifically. So if you have MetaTF on your system and need to bring in those models, you can do that with Edge Impulse. Or if you're starting from Edge Impulse and eventually need to go back to MetaTF for some specific things and reasons, you can do that as well. Then we have another question here regarding homophonic ciphers. Nikunj, I'm not sure if you can read this particular question. Is there any information about that with regarding Akida and BrainChip?
So I believe the question really is, I hope to use weighting within the image structure to decode the image. Are there any sources of information within your software or hardware? I'm not really sure if I know more about these homophonic ciphers here, but typically what Akida is meant to do is to run neural networks very efficiently. So if there's anything with regards to pre-processing, or if there's anything in regards to decoding a certain part of the image, that's kind of pre-Akida. So you can work with existing tools. I know TensorFlow is a very nice tool to even visualize how your pre-process functions work. So that's some of the tools that you can work with. If any, you require any weight extraction from your neural networks when it runs on Akida, or whatever outputs you get out of every layer when you run the neural networks on Akida, we provide all of that functionalities through MetaTF. And so that way, you can deploy the model on Akida. You can even extract a lot of information on a layer-to-layer basis, and then find out how it's behaving based on certain characteristics as well, right? You can also extract activity sparsity as well on a layer-to-layer basis, so you can get some of those information along with it.
Yeah, and then touching on the feature extraction as well. If you have a pre-processing step that needs to be done to images and things like that, BrainChip can bring that in and work with that inside the platform. So we have, if you're inside, Edge Impulse can bring that into the platform, right? So if you're inside a project and working on your DSP code, we call it bring your own DSP. It's more about bring your own processing code in general. So we've worked with customers who have done a lot of pre-processing for like radar data sets, time-of-flight sensors, anything that's maybe near image, but you're not necessarily displaying RGB values out of it. And then those, of course, can then be fed into Akida models or other models as well that you need to work with. And then Nikunj was talking about looking at where weight information as well. So if I look here at this job, we'll bring this up from this one. We have information about this kernel shape, and then we spit out information about number of MPs and things like that. So you can print information about your model when it gets converted from a traditional CNN to an SNN in the Edge Impulse output, so that you can see that information as you train your model as well, since we have MetaTF in the background. To do so, all you have to do is head over to the training portion of your project, switch over to expert mode, and then you can come in here and write the necessary steps to get out some of the information that you need for your particular model.
I see another question about pricing for the enablement kits. So again, we are able to provide enablement kits. If you visit shop.brainchip.com, that's where you'll be able to look for our kits and find out some pricing about our board and our kits that we have with a shuttle box or a Raspberry Pi kit. If there is any different need, you may contact us at sales@brainchip.com, and we can get you set up with one of our sales guys to make sure that you get the right pricing structure and understand your requirements, make sure we can adhere to your use cases.
I didn't have scroll down over here on the Q&A. I didn't see that one. Glad you saw that one.
Oh yeah.
Yeah. I was about to close it out early. Was there any other questions we wanted to address here? Nikunj, I'm just kind of looking through the list.
Right. I'm just seeing one more question here. Is there any reference design documentation on the website for interfacing with an STM32 running RTOS or similar? So I don't think there's a reference documentation on MetaTF about it. However, we do provide a source library code to make sure you can compile our engine library along with your application to run on your RTOS. So again, that's available through MetaTF. And if you search for deploy inside MetaTF, you may be able to get some information out there. But if there's some additional information that you require, please contact us and we can help you guys get set up with making sure that we understand your requirements and we can help you out with some specific user guides and documentation.
So Joshua, can I ask you a question?
Yeah.
So when I am training the pipeline, so for my particular project, vitamin detection, so I have collected all the samples like you've seen 5,000 from sample, 5,000, 6,000. So when I'm training the data set, it was like, normal, the data set which labels whatever I've collected. So is there any way or of augmenting the data? Is there any option that you guys are working on so that while training, so that it will get every aspect of the images?
Yeah, so we do a number of data augmentation options there. So if we go back to some basic classification, image classification stuff, you can flip on this checkbox here. And then we need to work with and enable that for FOMO for BrainChip, right? There's an equivalent checkbox for FOMO for other devices. We need to get that for BrainChip. And then if you need to do that basic data augmentation, it's the typical kind of things that you would see, right? So let's start, let's say you start with 10 images, and then what actually gets fed to your model, is maybe 40 images, but the 40 images are just variations of that first 10, where we stretched and skew and flipped, the image around. If you need to do something more custom, then you can always head into and download the Docker container for that block, right, for this learning block, and then write in some more data augmentation routines that might be more applicable for your particular situation. So in short, to answer the question, yeah, we do have some options there as a checkbox. We have some new features that we're working on with BrainChip to bring those to FOMO and some object detection models. And then if you need to do something custom, we have those abilities as well on the platform.
Thank you.
Great. I think we are close for time. And it looks like we've answered a lot of these questions already. So thank you very much, Nikunj, Sai, and Naveen. We really do appreciate y'all. It's been a pleasure working with you guys. And if you all need any more, if you have any more questions, please don't hesitate to reach out at hello@edgeimpulse.com or sales@brainchip.com. And please don't forget Imagine September 27th online. Thank you, everyone, and we hope you have a great day.
Thank you, everyone. Thank you, Josh.
Thanks, everyone.
Everyone.